to Bitcoin UTXO model. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into one of Bitcoin's most fundamental, yet often misunderstood, concepts, the UTXO model, which stands for Unspent Transaction Output. If you have ever wondered how Bitcoin actually tracks who owns what, you might assume it works like a bank account with balances, but it does not. Bitcoin uses a completely different approach that is more like handling physical cash with receipts. Understanding UTXO is crucial because it is the foundation of how Bitcoin prevents double spending, maintains security, and tracks ownership. This presentation will break down the UTXO model from first principles, using simple analogies and visual examples that make this complex topic accessible to everyone, whether you are a developer, investor, or just blockchain curious. The account model versus UTXO model. Before we dive into UTXO, let's understand what it's replacing. Most people are familiar with the account-based model used by traditional banks and systems like Ethereum. In the account model, each user has an account with a balance. When Alice sends money to Bob, the system simply deducts from Alice's balance and adds to Bob's balance. It's straightforward and intuitive because it mirrors how we think about money. However, Bitcoin takes a radically different approach with the UTXO model. Instead of tracking balances, Bitcoin tracks individual chunks of Bitcoin that haven't been spent yet. Think of it like this. The account model is like having money in a bank account where the balance updates, while the UTXO model is like carrying specific bills and coins in your pocket. Each bill has its own ID and history. You can't split a $20 bill in half. You have to spend the whole bill and get change back. This fundamental difference affects everything about how Bitcoin works, from transaction structure to privacy to security. What is a UTXO? So, what exactly is a UTXO? UTXO stands for Unspent Transaction Output. Let's break that down word by word. Unspent means it hasn't been used in another transaction yet, it's still available to be spent. Transaction output means it's the result of a previous transaction where someone sent Bitcoin. So, a UTXO is essentially a chunk of Bitcoin that was created by a previous transaction and is sitting there waiting to be spent. Every UTXO has two key properties: an amount of Bitcoin it contains, and ownership information specifying who can spend it. This ownership is defined by a locking script, usually requiring a digital signature from a specific public key. When you check your Bitcoin wallet and it shows you have 1 Bitcoin, what you really have is one or more UTXOs that add up to 1 Bitcoin. You might have 1 UTXO worth 1 Bitcoin, or you might have 10 UTXOs each worth 0.1 Bitcoin. Your wallet adds them all up to show your total spendable balance. Each UTXO is indivisible and atomic. It must be spent in its entirety in a transaction. You cannot spend half a UTXO if you need to send less than what a UTXO contains. You spend the entire UTXO and create a new UTXO as change back to yourself. How transactions create and consume UTXOs. Understanding how transactions work with UTXOs is essential for grasping the entire system. Every Bitcoin transaction has two main parts: inputs and outputs. Inputs are references to existing UTXOs that you are spending. Outputs are new UTXOs you are creating. When you create a transaction, you are essentially saying, I am taking these specific UTXOs as inputs, destroying them, and creating these new UTXOs as outputs. Let us walk through a concrete example. Imagine Alice has a UTXO worth 5 Bitcoin. She wants to send 2 Bitcoin to Bob. Alice creates a transaction with one input, her 5 Bitcoin UTXO. The transaction has two outputs. One output creating a 2 Bitcoin UTXO for Bob, and another output creating a 3 Bitcoin UTXO back to Alice as change. Once this transaction is confirmed, Alice's original 5 Bitcoin UTXO is consumed. It no longer exists and can never be used again. Now there are 2 new UTXOs. Bob's 2 Bitcoin UTXO and Alice's 3 Bitcoin UTXO. The old UTXO is spent, and the new UTXOs are unspent. This is the continuous cycle. UTXOs are consumed as transaction inputs and created as transaction outputs. The blockchain is essentially a massive ledger tracking which UTXOs have been created and which have been spent. UTXO set. Bitcoin's state. At any given moment in time, Bitcoin has what we call the UTXO set, which is the complete collection of all unspent transaction outputs. This UTXO set represents Bitcoin's current state. It is the answer to the question, who owns what Bitcoin right now? Every full Bitcoin node maintains this UTXO set in memory or on disk for quick access. When a new transaction comes in, nodes check the UTXO set to verify that the inputs being spent actually exist and have not been spent before. This is how Bitcoin prevents double spending. If someone tries to spend the same UTXO twice, the second transaction will reference a UTXO that is no longer in the UTXO set, and nodes will reject it. The UTXO set is dynamic. It constantly changes as new blocks are added. When a block is mined, the transactions in that block consume some UTXOs and create new ones. The UTXO set is updated by removing the spent UTXOs and adding the newly created ones. As of recent counts, the Bitcoin UTXO set contains over 100 million individual UTXOs representing all the Bitcoin in existence. This set is relatively compact, only a few gigabytes, when compared to the entire blockchain history, which is hundreds of gigabytes. This efficiency is one advantage of the UTXO model. Transaction inputs and unlocking scripts. Let's dig deeper into how transaction inputs work. When you want to spend a UTXO, you create a transaction input that references that specific UTXO. This reference includes 2 pieces of information: the transaction ID where the UTXO was created, and the output index number within that transaction. Think of it as an address pointing to exactly which UTXO you're spending. But referencing the UTXO is not enough. You also need to prove you have the right to spend it. This is where unlocking scripts come in. Every UTXO has a locking script that specifies the conditions for spending it. Typically, this locking script says, this UTXO can only be spent by providing a valid signature from this specific public key. To spend the UTXO, your transaction input must include an unlocking script that satisfies the locking script's conditions. In the typical case, the unlocking script contains your digital signature and public key. When nodes validate your transaction, they execute the unlocking script together with the locking script. If the scripts execute successfully, meaning your signature is valid and matches the required public key, the UTXO can be spent. This script system is actually quite powerful and flexible, allowing for complex spending conditions, but the simple signature verification case covers the vast majority of Bitcoin transactions. Transaction outputs and locking scripts. Now let's look at the output side. When you create a transaction output, you're creating a new UTXO that specifies 2 critical things: how much Bitcoin it contains, and the conditions for spending it. The amount is straightforward. It is the number of satoshis in the UTXO. Remember, a satoshi is the smallest unit of Bitcoin, 100 millionth of a Bitcoin. The spending conditions are defined by the locking script. In most cases, this locking script says, to spend this UTXO, you must provide a signature from this specific public key. The locking script contains a hash of the recipient's public key, often called a public key hash or address. This is what Bitcoin addresses represent. They are encoded versions of public key hashes that specify who can spend the UTXO. When you send Bitcoin to someone's address, you are creating a new UTXO with a locking script that only that person's private key can unlock. There are different types of locking scripts for different use cases. Pay to public key hash is the most common. used for regular Bitcoin addresses. Pay-to-script hash allows for more complex spending conditions, like multi-signature wallets. Pay-to-witness public key hash is used for SegWit addresses, offering better efficiency. But regardless of the specific type, all locking scripts serve the same fundamental purpose: defining who can spend the UTXO and under what conditions. Transaction fees and the UTXO model. Transaction fees in Bitcoin work elegantly with the UTXO model through a simple principle: the difference between inputs and outputs. Here's how it works. When you create a transaction, you select UTXOs as inputs that add up to at least the amount you want to send. Then you create outputs, one to the recipient, and usually one back to yourself as change. The transaction fee is whatever's left over. It's the amount not explicitly claimed by any output. For example, if you have inputs totaling 1 Bitcoin and you create outputs totaling 0.999 Bitcoin, the missing 0.001 Bitcoin becomes the transaction fee that goes to the miner. This is important. There's no explicit fee field in Bitcoin transactions. The fee is implicit, calculated as the sum of input values minus the sum of output values. This means you need to be careful when constructing transactions. If you accidentally create outputs that don't add up to your inputs, whatever's left over becomes the fee. There have been cases where people accidentally paid enormous fees because they forgot to include a change output. Miners collect these fees as a reward for including transactions in blocks. The fees incentivize miners to process transactions and secure the network. As block rewards decrease over time through halvings, transaction fees become increasingly important for Bitcoin's security model. Preventing double spending with UTXOs. One of Bitcoin's greatest achievements is solving the double spending problem without a central authority, and the UTXO model is central to this solution. Double spending means using the same Bitcoin twice. This means spending it once to buy something, then spending it again elsewhere before the first transaction confirms. Here is how the UTXO model prevents this. Each UTXO can only be spent once, ever. Once a transaction spending a UTXO is included in a block and confirmed, that UTXO is removed from the UTXO set. It is gone, consumed, no longer exists. If someone tries to create a second transaction spending the same UTXO, every node will check the UTXO set and find that the UTXO is already spent. The transaction will be rejected as invalid. This is fundamentally different from an account model where you might try to send the same balance twice. With UTXOs, you are referencing specific outputs that either exist or do not exist. There is no ambiguity. The blockchain's consensus mechanism determines which transaction gets confirmed first. If two conflicting transactions try to spend the same UTXO, only one can be included in the blockchain. Whichever transaction gets into a block first wins, and the other becomes permanently invalid. This clear, unambiguous state is what makes Bitcoin's double spending prevention so robust. The UTXO model combined with blockchain consensus creates a system where double spending is cryptographically and economically infeasible. UTXO selection and coin control. When you send a Bitcoin transaction, your wallet needs to decide which UTXOs to use as inputs. This process is called UTXO selection or coin control, and it is more complex than you might think. Your wallet contains multiple UTXOs from various past transactions. When you want to send an amount, the wallet must choose which UTXOs to combine to cover that amount plus fees. Different selection strategies exist. The simplest is first in, first out, spending the oldest UTXOs first. Another is largest first, using the biggest UTXOs to minimize the number of inputs. There is also a random selection strategy for better privacy. Advanced wallets offer manual coin control, letting users choose exactly which UTXOs to spend. Why does this matter? Several reasons. First, privacy. Combining UTXOs from different sources can link addresses together, revealing that they belong to the same person. Second, fees. Transactions with many small inputs cost more in fees than transactions with fewer large inputs, because each input adds data to the transaction. Third, UTXO management. If you receive many small payments, you accumulate many small UTXOs, sometimes called dust. Consolidating these during low fee periods by combining them into larger UTXOs makes sense. Some wallets automatically consolidate UTXOs when fees are low. Understanding UTXO selection helps you manage your Bitcoin more efficiently, minimize fees, and maintain better privacy. It is an often overlooked aspect of practical Bitcoin usage that can significantly impact your experience. Change outputs and address reuse. Change outputs are a crucial but often misunderstood part of Bitcoin transactions. Remember, UTXOs must be spent entirely. You cannot spend a fraction of a UTXO, so when you need to send an amount smaller than your UTXO, you create two outputs, one to the recipient, and one back to yourself as change. This change output is just like any other UTXO. It is locked to an address you control. Here is where best practices come in. You should never reuse addresses in Bitcoin. Each change output should go to a new, unused address. Why? Privacy and security. If you reuse the same address for change, anyone looking at the blockchain can track your transactions by following that address. They can see your balance, your spending patterns, your transaction history. By using a new address for each change output, you break this chain of linkability. Modern wallets handle this automatically using hierarchical deterministic wallets. These wallets can generate unlimited new addresses from a single seed phrase. When you receive Bitcoin or get change, the wallet automatically generates a fresh address. Users do not even see this happening. It is transparent. But this simple practice of using fresh addresses for change dramatically improves Bitcoin's privacy characteristics. Without it, the transparent blockchain would make every user's financial activity an open book. Change outputs also affect transaction size and fees. A transaction with change requires an extra output, adding about 34 bytes. But this is usually unavoidable, unless you have a UTXO that exactly matches your payment amount plus fees, which is rare. Understanding change outputs helps you interpret what is happening when you look at Bitcoin transactions on a block explorer. UTXO privacy considerations. Privacy in Bitcoin is a complex topic, and the UTXO model has both advantages and disadvantages for privacy. On one hand, Bitcoin's transparency means every transaction is visible on the blockchain. When you combine multiple UTXOs as inputs in a transaction, you are revealing that all those UTXOs likely belong to the same person. This is called common input ownership heuristic, one of the primary methods for blockchain analysis. If UTXOs from addresses A, B, and C are used as inputs in the same transaction, analysts assume all three addresses belong to the same entity. This can de-anonymize users. On the other hand, the UTXO model allows for privacy-enhancing techniques. Coin-join transactions let multiple users combine their transactions, mixing their UTXOs together so observers cannot tell which inputs correspond to which outputs. Each user gets new UTXOs back, but the linkage is broken. Services like Wasabi Wallet and Samurai Wallet implement coin-join to improve privacy. Another technique is using different UTXO sizes. If all your UTXOs are round numbers, it might indicate they came from the same source. Varying UTXO amounts makes chain analysis harder. There is also the concept of UTXO consolidation timing. Consolidating UTXOs during high activity periods makes your transaction less noticeable than doing it when the mempool is empty. However, perfect privacy in Bitcoin is challenging because the UTXO model creates a permanent public record. Every UTXO's history is traceable back through the blockchain. Privacy requires constant vigilance and careful UTXO management. Projects like Taproot improve privacy by making complex transactions look identical to simple ones, reducing information leakage from the UTXO set. Multi-signature UTXOs. Multi-signature UTXOs represent one of Bitcoin's most powerful features, enabled by its flexible scripting system. While most UTXOs require only a single signature to spend, multi-signature or multisig UTXOs require multiple signatures from different keys. For example, a 2 of 3 multisig UTXO requires any 2 signatures out of 3 possible keys. This is incredibly useful for shared funds, corporate treasuries, or enhanced security. Here's how it works. When creating a multisig UTXO, the locking script specifies multiple public keys and a threshold, for example, 2 of 3 or 3 of 5. To spend this UTXO, the transaction input must provide signatures from at least the threshold number of private keys. Bitcoin's scripting language verifies that the required number of valid signatures are present. Multisig use cases are diverse. For personal security, you might create a 2 of 3 setup with keys on your phone, laptop, and hardware wallet. If one device is compromised or lost, you still have 2 others. For businesses, a 3 of 5 setup might require the CEO plus any 2 board members to approve large payments. For escrow services, a 2 of 3 setup with buyer, seller, and arbiter ensures fair transactions. The arbiter only signs if there's a dispute. There are different technical implementations. Pay-to-script hash, or P2SH, was the original method, wrapping the multisig script in a hash. Pay-to-witness script hash, or P2WSH, is the SegWit version, offering lower fees. More recently, Taproot enables more complex spending conditions while looking like single-signature UTXOs on the blockchain, improving privacy. Multisig UTXOs demonstrate how the UTXO model's flexibility enables sophisticated security models without requiring changes to the base protocol. Time-locked UTXOs. Bitcoin's UTXO model also supports time-locked outputs, allowing you to create Bitcoin that cannot be spent until a certain time in the future. This powerful feature enables various use cases, from inheritance planning to payment channels. There are 2 types of time locks. Absolute time locks specify an exact block height or timestamp before which the UTXO cannot be spent. For example, you could create a UTXO that becomes spendable at a specific block height, or on January 1, 2026. Relative time locks specify a delay from when the UTXO was created, like 1,000 blocks after the UTXO was confirmed, or about 1 week. Time locks are implemented in 2 ways. Check Lock Time Verify, or CLTV, is an absolute lock embedded in the UTXO's locking script. The UTXO simply cannot be spent until the specified time. Check Sequence Verify, or CSV, implements relative locks, also in the locking script. There's also transaction-level time locks using the nlock time field, though these work differently and are less commonly used for UTXOs. Practical applications of time-locked UTXOs include inheritance planning. You can send Bitcoin to your heirs in a time-locked UTXO that they can access after a certain date, providing a dead man's switch. Escrow services use time locks to create refunds. If a transaction isn't confirmed within a timeframe, the funds automatically return to the sender. The Lightning Network relies heavily on time-locked UTXOs to secure payment channels, ensuring parties can recover funds if the other party becomes unresponsive. Subscription services could use time locks to lock up funds that get released periodically to the service provider. Time-locked UTXOs add a temporal dimension to Bitcoin, transforming it from a simple payment system to a platform for complex financial contracts that unfold over time. UTXO set size and blockchain scaling. The UTXO set size has important implications for Bitcoin's scalability and node operation. Remember, every full node needs to maintain the complete UTXO set to validate transactions. As Bitcoin grows, this set grows too, creating storage and memory requirements. Currently, the UTXO set contains over 100 million UTXOs, occupying several gigabytes. Each UTXO in the set requires storage: the transaction ID, output index, amount, and locking script. Multiply this by hundreds of millions of UTXOs, and you have significant resource requirements. This affects node operators who need fast access to the UTXO set to validate transactions quickly. UTXO set growth is affected by user behavior. Creating many small outputs bloats the set. Consolidating UTXOs during low fee periods helps. The concept of UTXO dust is relevant here. Very small UTXOs worth less than the cost to spend them. These clutter the UTXO set indefinitely since they are economically unspendable. Bitcoin has dust limits that discourage creating tiny UTXOs. Scaling proposals must consider UTXO set growth. Increasing block size means more transactions, potentially creating more UTXOs faster. This is one reason why blockchain scaling is complex. It is not just about block size, but also about the downstream effects on the UTXO set. Some proposals suggest UTXO set commitments, where the set is periodically hashed and committed to in the blockchain. This would allow new nodes to start from a UTXO set snapshot without validating the entire history, though this has trust trade-offs. Technologies like the Lightning Network help by moving many transactions off-chain, reducing UTXO set growth. When Lightning channels are opened and closed, they create relatively few UTXOs compared to individual transactions. Understanding UTXO set dynamics is crucial for Bitcoin developers working on scaling solutions and for node operators managing resources. Coinbase transactions and UTXO creation. Every Bitcoin block contains a special transaction, called the Coinbase transaction, that differs from regular transactions in how it interacts with UTXOs. While normal transactions consume existing UTXOs and create new ones, the Coinbase transaction creates new Bitcoin from nothing. This is how new Bitcoin enters circulation through mining rewards. The Coinbase transaction has no inputs, or rather, its input is a special null input that does not reference any existing UTXO. Instead, it creates outputs containing the block reward, which currently is 3.125 Bitcoin after the 2024 halving, plus all the transaction fees from transactions in that block. These outputs are the miner's payment for mining the block. However, Coinbase transaction outputs have a special restriction. They cannot be spent until 100 blocks have been mined on top of the block containing them. This maturity rule prevents miners from spending rewards from blocks that might be orphaned if a blockchain reorganization occurs. It ensures the blockchain has stabilized before reward UTXOs become spendable. After 100 confirmations, roughly 17 hours, Coinbase UTXOs behave just like any other UTXO. The miner can spend them in transactions, combine them with other UTXOs, split them into smaller amounts, and so on. Coinbase transactions are the only source of new Bitcoin, making them special in the Bitcoin protocol. They are also historically interesting. The first Coinbase transaction in the Genesis block created Satoshi Nakamoto's initial 50 Bitcoin reward. That UTXO has never been spent and likely never will be, serving as a permanent monument. Coinbase transactions also contain arbitrary data fields that miners use for various purposes. For example, Satoshi embedded a newspaper headline in the Genesis block's Coinbase to prove the date. Understanding Coinbase transactions shows how the UTXO model accommodates the special case of creating new currency while maintaining the system's overall consistency and security. UTXO versus account model. Trade-offs. Let's directly compare the UTXO model to the account model used in systems like Ethereum to understand the trade-offs. The account model is simpler conceptually. Each address has a balance that increases and decreases with transactions. It is how banking works, so it is intuitive. The UTXO model is more complex, tracking individual outputs rather than balances. So, why does Bitcoin use it? First, parallelization. In the UTXO model, different transactions spending different UTXOs are completely independent. They can be validated in parallel since there is no shared state to update. In the account model, transactions affecting the same account must be processed sequentially to maintain correct balances. Second, transaction verification is simpler with UTXOs. To verify a transaction, you just check that the UTXOs being spent exist in the UTXO set. In the account model, you need to verify the account has sufficient balance, which might require checking recent transactions. Third, privacy. UTXOs can be more private because different UTXOs can be used separately, reducing linkability. In the account model, all transactions go through one balance, making tracking easier. However, the account model has advantages too. Smart contracts are more natural. Contracts have state that updates, which fits the account model. That is why Ethereum chose it. The account model also avoids the change output complexity and UTXO management burden. For simple payments, accounts are cleaner. Storage efficiency differs depending on usage patterns. Account models store less data per user but struggle with high-frequency trading. UTXO models can bloat with many small outputs but handle concurrency better. Neither model is universally better. They are optimized for different priorities. Bitcoin's choice of UTXOs reflects its focus on security, verifiability, and parallel processing over smart contract complexity. Understanding these trade-offs helps you appreciate why different blockchains make different design choices. Wallet software and UTXO management. Modern Bitcoin wallets hide much of the UTXO complexity from users, but understanding what is happening under the hood helps you use Bitcoin more effectively. When you open your wallet, it scans the blockchain for UTXOs belonging to your addresses. It adds up these UTXOs to show your balance. This scan can take time for new wallets, as they need to check the entire blockchain history for their addresses. This is why importing an old seed phrase into a new wallet requires waiting while it scans. Different wallet types handle UTXOs differently. Full node wallets like Bitcoin Core maintain the complete UTXO set locally. They can validate transactions and UTXOs independently without trusting anyone. SPV wallets, or simplified payment verification wallets, do not maintain the full UTXO set. They ask full nodes for information about their UTXOs. This is lighter but requires some trust. When you send a transaction, your wallet performs several UTXO-related tasks. First, UTXO selection, choosing which UTXOs to spend as inputs. Second, calculating fees based on transaction size, which depends on the number of inputs and outputs. Third, creating a change output to a new address. Fourth, signing the transaction with the private keys corresponding to the UTXOs being spent. Advanced wallets offer coin control features, letting you manually select UTXOs. This is useful for privacy-conscious users who want to avoid linking certain UTXOs together. Some wallets show UTXO age and size, helping you make informed decisions. Wallet recovery from seed phrases works because deterministic wallet schemes can regenerate all your addresses from the seed. The wallet scans for UTXOs belonging to those addresses. This is why you can restore your entire balance just from 12 or 24 words. Understanding your wallet's UTXO management helps you troubleshoot issues, such as why a transaction has a certain fee or why your balance looks different than expected. It demystifies what your wallet software is doing behind its user-friendly interface. Advanced UTXO concepts and future developments. As Bitcoin evolves, the UTXO model continues to enable new capabilities through upgrades and second-layer technologies. Let's explore some advanced concepts. Taproot, activated in 2021, revolutionized UTXO scripts. It allows complex spending conditions to look identical to simple single-signature spends on the blockchain. A multi-sig UTXO, a lightning channel, or a complex contract all look the same. This dramatically improves privacy and efficiency. Taproot UTXOs can have multiple spending paths, a key path for cooperative spending and a script path for fallback conditions. UTXO commitments are a proposed enhancement where the UTXO set is periodically committed to the blockchain through a hash. This would enable assumable-valid UTXO set bootstrapping. New nodes could start from a recent UTXO set snapshot rather than validating from Genesis. This would dramatically speed up initial node sync while maintaining security through hash commitments. The Lightning Network builds on UTXOs through payment channels. Two parties create a multi-sig UTXO, then transact off-chain by updating the distribution of that UTXO. Only the channel opening and closing transactions touch the blockchain, making thousands of payments from two UTXOs. Coin-join protocols use carefully coordinated transactions where multiple parties create a transaction together, mixing their UTXOs. This breaks the common input ownership heuristic, improving privacy. State chains are a proposed technology for transferring UTXO ownership off-chain. The actual UTXO stays on the blockchain, but ownership changes hands through signed attestations, only settling on-chain when necessary. RGB and Taro protocols enable tokens and assets on Bitcoin by attaching additional data to UTXOs through cryptographic commitments. The UTXO remains a normal Bitcoin UTXO on-chain, but carries additional meaning in the RGB protocol. These developments show that the UTXO model, while designed for Bitcoin's original simple payment use case, is flexible enough to support sophisticated financial applications that Satoshi never imagined. Conclusion and key takeaways. Let's recap the essential concepts about Bitcoin's UTXO model. Unlike account-based systems, Bitcoin does not track balances. It tracks individual chunks of Bitcoin called unspent transaction outputs. Each UTXO has an amount and spending conditions defined by locking scripts. Transactions consume UTXOs as inputs and create new UTXOs as outputs, continuously recycling Bitcoin through the system. The UTXO set represents Bitcoin's current state, all spendable Bitcoin. Every full node maintains this set to validate transactions and prevent double spending. When a UTXO is spent, it is removed from the set forever, making double spending impossible. UTXO management affects privacy, fees, and transaction efficiency. Wallet software handles most of this automatically, but understanding UTXOs helps you use Bitcoin more effectively. Advanced features like multisig, time locks, and taproot leverage the UTXO model's flexibility to enable sophisticated use cases beyond simple payments. The UTXO model is fundamental to Bitcoin's security, enabling parallel validation and clear transaction semantics. While more complex than account models, it is optimized for Bitcoin's priorities of security, verification, and decentralization. Understanding UTXOs transforms Bitcoin from a mysterious digital currency into a logical, well-designed system. You now know what is really happening when you send or receive Bitcoin. UTXOs being consumed and created in an endless chain stretching back to the Coinbase transaction that first created those Satoshis. This knowledge empowers you to use Bitcoin more intelligently, whether you are a developer building on Bitcoin, an investor managing holdings, or simply someone curious about how cryptocurrency actually works at a technical level. Thank you for your attendance. Please consider subscribing to the channel.